You think you know what nothing is. You're wrong. Completely, fundamentally, beautifully wrong. And Richard Feynman, one of the greatest physicists who ever lived, can prove it to you in a way that will absolutely wreck your intuition about reality. Here's what you think nothing is. Empty space, a vacuum, the absence of stuff. You imagine a box, you take everything out of it, and what's left is nothing. Simple, right? Wrong. So incredibly wrong that when you understand what nothing actually is, you'll realize that the universe is far stranger than you ever imagined. Let me start with something Feynman loved to do. He loved to take ideas that seemed obvious and show you why they're nonsense. And nothing, the concept of pure emptiness, was one of his favorites, because it gets to the heart of what reality actually is. Here's the first problem with your idea of nothing. You can't actually make it. You literally cannot create nothing. Not because you lack the technology, not because you don't have a good enough vacuum pump, but because nothing cannot exist. Think about that for a second. Nothing cannot exist. That sounds like a contradiction, like word games. But it's not. It's one of the deepest truths in physics. Let me show you what I mean. Imagine you have a box, a perfect box, perfectly sealed, and you start removing things from it. You pump out all the air, every nitrogen molecule, every oxygen atom, gone. You remove all the radiation, all the light, every photon, gone. You cool it down to absolute zero so there's no thermal energy. You shield it from every external force, every vibration, every field. You remove everything, absolutely everything. Now, what's inside that box? Your intuition says nothing. Empty space, pure vacuum. But here's what Feynman would tell you. That box is absolutely full, packed, teeming with activity, more activity than you can possibly imagine. And this isn't speculation. This isn't philosophy. This is measurable, observable, experimentally verified reality. Here's what's actually in your empty box. First, there's the quantum vacuum. And the quantum vacuum is anything but empty. It's a boiling sea of virtual particles, constantly appearing and disappearing, popping into existence and vanishing again, billions of times per second in every cubic centimeter of space. Wait, particles appearing from nothing? How does that work? Here's where we need to talk about one of Feynman's most important insights, something he spent his career developing. The Heisenberg uncertainty principle. You've probably heard of it. Most people think it's about measurement, about how observing something changes it. That's not quite right. The uncertainty principle is deeper than that. It's about reality itself. And one version of it says this: energy and time are linked in a strange way. The more precisely you know when something happens, the less precisely you can know its energy. And here's the key. If you look at a small enough time interval, energy becomes completely uncertain, completely undefined. What does that mean? It means that for incredibly brief moments, the universe can borrow energy from nowhere. Energy can just appear, violate conservation of energy, pop into existence out of the vacuum. But there's a catch. The energy has to pay itself back. The universe can borrow energy, but only for a time inversely proportional to how much energy it borrowed. Borrow a little, you can keep it longer. Borrow a lot, you have to give it back almost instantly. This is real. This actually happens. And Feynman was one of the people who figured out exactly how it works. These energy fluctuations in the vacuum create particle pairs. An electron and its antimatter partner, a positron, pop into existence. They exist for a tiny fraction of a second. Then they collide and annihilate, paying back the energy debt. This happens everywhere, all the time, in what you think of as empty space. Now, you might be thinking this sounds like theoretical nonsense, just mathematics. Just equations with no connection to reality. But here's the thing. We can measure it. We have measured it. There's an experiment called the Casimir effect that proves the vacuum is full of these virtual particles. Here's how it works. You take two metal plates, perfectly smooth, perfectly parallel, and you put them incredibly close together in a vacuum. What happens? The plates are pushed together by a measurable force. Why? Because between the plates, only certain virtual particles can exist. The gap is so small that only particles with certain wavelengths can fit, but outside the plates, all virtual particles can exist. So there's more quantum activity, more pressure from the vacuum outside than inside. The vacuum pushes the plates together. This has been measured. This is not theory. This is experimental fact. The vacuum has pressure. Empty space pushes on things. Nothing has properties. That should blow your mind. Nothing has measurable effects. Nothing exerts force. Nothing is something. But wait, there's more, much more. Because virtual particles are just the beginning. Feynman showed us something even stranger about the vacuum. It's not just full of particles. It's full of fields. Quantum fields that exist everywhere, permeating all of space, whether there's matter there or not. Let me explain what a field is, because this is crucial. A field is something that has a value at every point in space. Temperature is a field. At every location in this room, there's a temperature. You can map it. You can measure it at different points. The temperature field fills the room. Electromagnetic fields work the same way. At every point in space, there's an electric field value and a magnetic field value. Even if there's no charge there, even if there's no magnet, the field still exists. Now, here's what Feynman and others discovered. There are quantum fields for everything. There's an electron field that fills all of space. There's a quark field. There's a photon field. Every type of particle has a corresponding field, and these fields exist everywhere, always, even in your supposedly empty box. What are particles then? This is where it gets beautiful. Particles are excitations in their fields. A ripple in the electron field is what we see as an electron. A ripple in the photon field is what we see as light. The particle is not a little ball bouncing around. The particle is a localized vibration in a field that exists everywhere. Think about that. The electron in your body right now is not a thing traveling through space. It's a disturbance in the electron field, which fills the entire universe. You are made of ripples in fields. Everything is ripples in fields, and the fields are always there, even when they're not rippling. So what's the ground state of these fields? What happens when there are no particles, no ripples, no excitations? You'd think the field just sits there at zero, perfectly still, perfectly quiet. That would be nothing, right? Wrong. Quantum mechanics says, no, the field cannot sit at zero. It cannot be perfectly still. Because of the uncertainty principle, again. If the field were exactly zero, you'd know its value precisely, and you'd know its rate of change precisely. But quantum mechanics forbids that. You cannot know both with perfect precision. So the field has to fluctuate. Even in its ground state, even with no particles present, the field jiggles and vibrates and oscillates around zero. These are called zero-point fluctuations. The vacuum energy, the energy of nothing. This isn't optional. This isn't something that might happen. This is required by the fundamental laws of physics. Empty space must have energy. Nothing must be something. The vacuum must fluctuate. And here's the crazy part. When you add up all these zero-point fluctuations from all the different quantum fields that fill space, you get an enormous amount of energy, stupendously enormous. Some calculations suggest the vacuum energy density should be huge, far bigger than the energy density of matter. Now, there's a problem here, a big problem. We don't observe this much vacuum energy. If space had that much energy, the universe would look completely different. This is called the cosmological constant problem, and it's one of the biggest unsolved mysteries in physics. But the point is, even the lowest estimates of vacuum energy are not zero. The vacuum has energy. Nothing has energy. Let me tell you about something else Feynman loved. He loved quantum electrodynamics, QED for short. He won the Nobel Prize for his work on it. And QED gives us one of the most precise predictions in all of science, matching experiments to 10 decimal places. What does QED tell us about the vacuum? It tells us that empty space is absolutely seething with electromagnetic fields, constantly fluctuating, constantly creating and destroying virtual photons. These virtual photons have real effects. They cause measurable changes in atoms. There's something called the Lamb shift, a tiny difference in energy levels of electrons in a hydrogen atom that's caused entirely by interactions with virtual photons in the vacuum. Feynman helped calculate this. The prediction matches the measurement perfectly. Empty space, the vacuum, nothing, is interacting with atoms and changing their properties in measurable ways. Here's another one. The magnetic moment of the electron. This is a measure of how the electron behaves like a tiny magnet. QED predicts a value for this that includes contributions from virtual particles in the vacuum, particles that pop in and out of existence, affecting the electron. The theoretical prediction matches experimental measurements to 11 decimal places. 11. That's one of the most precise agreements between theory and experiment in all of science. And it absolutely requires that the vacuum be full of quantum activity. Now, let's talk about something that will really mess with your head. Feynman diagrams. You've probably seen them. Little drawings with lines and squiggles that physicists use to calculate particle interactions. Feynman invented them, and they're brilliant because they turn impossibly complex quantum calculations into pictures you can draw. But here's what those diagrams actually represent. Every line is a particle. Every point where lines meet is an interaction. Simple, right? But look closer. Some of those diagrams have loops, particles that appear and disappear, virtual particles from the vacuum. When you calculate the probability of an electron scattering off a photon, you don't just draw one diagram. You draw every possible diagram, including ones with loops, with virtual particles appearing from nothing and vanishing again. And all of those diagrams contribute. All of those virtual particles affect the result. You cannot calculate the behavior of real particles without including the contributions from virtual particles, from fluctuations in the vacuum, from nothing. Nothing is part of every physical process. Nothing participates in everything that happens. Let me give you a concrete example. When two electrons repel each other, you think of them as feeling an electromagnetic force, right? But what's actually happening? In the Feynman picture, one electron emits a virtual photon, a photon that doesn't have the right energy to exist, a photon that's borrowed from the vacuum. That virtual photon travels to the other electron and gets absorbed. The exchange of this virtual particle is what causes the force. But it's not just one virtual photon. It's every possible virtual photon, and every possible pair of virtual photons, and every possible combination of virtual particles emerging from the vacuum, interacting with the electrons, and disappearing back into the vacuum. When you sum up all of these contributions from nothing, from the quantum vacuum, you get the force between electrons. Nothing mediates the force between everything. Now, here's something Feynman explained beautifully. You cannot remove the vacuum. You cannot get rid of these quantum fields. You cannot stop the fluctuations. Even if you could remove all matter, all radiation, all energy, the fields would still be there, still fluctuating, still full of zero-point energy. The vacuum is a fundamental feature of reality. It's not the absence of something. It's a thing in itself. Think about what this means. Before there were atoms, before there were particles, before there was anything, there were quantum fields. The fields are more fundamental than the particles. The fields are what's real, and particles are just what happens when fields get excited. So even if you imagine the universe before the Big Bang, before there was any matter or energy, there would still be quantum fields, still be a vacuum, still be fluctuations. There has never been nothing. There can never be nothing. But wait, let's go deeper, because Feynman had more to say about this. He talked about something called quantum foam. At the smallest scales, scales far smaller than atoms, smaller than nuclei, at the Planck scale, around 10 to the minus 35 meters, space-time itself becomes uncertain. Remember, quantum mechanics is about uncertainty. Position is uncertain. Energy is uncertain. Time is uncertain. But if time and space are uncertain, then space-time itself must fluctuate. At incredibly small scales, the smooth fabric of space-time that we experience breaks down into a boiling, fluctuating foam. Tiny wormholes appearing and disappearing. Virtual black holes popping in and out of existence. The geometry of space itself becoming undefined. This is speculative. We can't measure it directly, but it follows from combining quantum mechanics with general relativity. And if it's true, it means that even space-time, the stage on which everything happens, is not nothing when empty. It's a dynamic, fluctuating, quantum mechanical thing. Nothing cannot exist because even the emptiest space is quantum space-time foam. Let me tell you something Feynman said. He said that understanding quantum mechanics means accepting that your common sense is wrong, that your intuition, built from everyday experience, will mislead you at the quantum level, and nothing is a perfect example. You think nothing is simple. It's not. You think nothing is passive. It's not. You think nothing is the absence of everything. It's not. Nothing is active. Nothing has structure. Nothing has energy. Nothing fluctuates and bubbles and seethes with quantum activity. Nothing is fundamental to everything. Here's another way to think about it. In classical physics, before quantum mechanics, you could imagine taking away all the energy from a system, cool it to absolute zero, stop all motion, reach a state of perfect stillness. That would be nothing. No energy, no motion, no activity. But quantum mechanics says you cannot do that. The uncertainty principle forbids it. If you perfectly localized a particle, stopped it completely, you'd know its position and momentum exactly, which is impossible. So particles must always have some motion, some energy, even at absolute zero. This is called zero-point energy. Even the coldest possible system has energy. Even nothing has energy. And this isn't just theoretical. Scientists have cooled things to billionths of a degree above absolute zero, and even at those temperatures, quantum fluctuations are measurable. Atoms still move. Fields still fluctuate. There is no state of perfect rest. There is no state of nothing. Now, let me talk about what might be the strangest part of all. The vacuum can decay. This is a prediction from quantum field theory. The vacuum we live in, the ground state of all the fields, might not be the true ground state. It might be a false vacuum, a metastable state that could decay to a lower energy state. If that happened, a bubble of true vacuum would form somewhere in the universe and expand at the speed of light, converting everything it touches to the new vacuum. The laws of physics inside that bubble could be completely different. Particles could have different masses. Forces could have different strengths. Everything would change. This is called vacuum decay, and it's terrifying because it would be completely unpredictable, impossible to see coming, and would destroy everything in its path. The vacuum, nothing, empty space could spontaneously change into a different kind of nothing that's incompatible with our existence. Nothing is unstable. Nothing could kill us all. But here's the thing, and Feynman would appreciate this. The very fact that we're having this conversation means that either our vacuum is stable or vacuum decay hasn't happened in our region of the universe yet. We exist because nothing has remained consistently nothing for the entire history of the cosmos. The stability of empty space is why we're here. Let me tell you about one more thing. Feynman had a way of thinking about particles that's completely backwards from how you normally think. He said that an electron moving forward in time is mathematically identical to a positron, an anti-electron, moving backward in time. This sounds like nonsense, but it's a real feature of the equations. What does this mean for the vacuum? It means that when a virtual electron-positron pair pops out of the vacuum, you can think of it as a single electron briefly moving backward in time, before moving forward again. The vacuum isn't creating two particles, it's causing one particle to zigzag through time. Virtual particles in the vacuum might be real particles taking detours through time. This is the kind of thing that made Feynman brilliant. He could look at equations and see stories, see possibilities, see interpretations that nobody else thought of. And his point was always the same. The math works. The predictions are correct. But what it means, what's actually happening, is far stranger than our everyday intuition can grasp. Here's what I want you to understand. Nothing is not simple. Nothing is not empty. Nothing is the quantum vacuum, a state of lowest energy but not zero energy, a boiling sea of virtual particles and fluctuating fields, a substrate that exists everywhere and always, a fundamental feature of reality that cannot be removed or destroyed or even properly defined without quantum mechanics. Every atom in your body is surrounded by vacuum. Every particle is embedded in quantum fields. Every force is mediated by virtual particles from nothing. You are not separate from the vacuum. You are patterns of excitation in the same fields that fill empty space. You are intimately connected to nothing, because nothing is what you're made of. When Feynman talked about this, he had a sense of wonder about it. Here we are, made of quantum fields, surrounded by vacuum, living in a universe where empty space is full and nothing is something. And we figured it out. We developed mathematics that describes it. We did experiments that confirm it. We understand nothing. That should amaze you. Tiny creatures of a small planet, using brains that evolved to throw rocks and find food, managed to understand the quantum vacuum. We looked at empty space and discovered it's not empty. We looked at nothing and found everything. But here's the hard part, and Feynman was always honest about this. We don't understand everything, not even close. The cosmological constant problem, the vacuum energy problem, is still unsolved. We can calculate what the vacuum energy should be, and we're off by 120 orders of magnitude. That's not a small error. That's the worst prediction in the history of physics. Something is deeply wrong with our understanding. Either our calculation is wrong, or something is cancelling out the vacuum energy, or we're missing something fundamental about how quantum field theory and gravity work together. We know the vacuum has properties. We know it affects particles. We know it has energy. But we don't know how much, or why, or what it means for the large-scale structure of the universe. And there's another mystery: dark energy. About 70% of the universe is made of something we call dark energy, an energy that fills space uniformly and causes the expansion of the universe to accelerate. Is dark energy the vacuum energy? Is it the cosmological constant? Is it something else entirely? We don't know. The most abundant thing in the universe, and we have no idea what it is. It might be a property of nothing. It might be nothing itself. Here's what Feynman would tell you. It's okay not to know. It's okay to have mysteries. The joy is in the puzzle, in the questioning, in the attempt to understand. What's not okay is pretending you understand when you don't. What's not okay is accepting simple answers when reality is complex. So when someone asks you what nothing is, don't say it's the absence of everything. Don't say it's empty space. Say it's the quantum vacuum. Say it's the ground state of quantum fields. Say it's zero-point fluctuations and virtual particles and Casimir forces and vacuum energy. Say it's something we partially understand and partially don't. Say it's one of the most interesting things in physics. Let me bring this all together because we've covered a lot of ground, and I want the picture to be clear. Nothing is not nothing. Empty space is not empty. The vacuum is full of quantum fields, all at their ground state, all fluctuating due to uncertainty, all contributing energy to empty space. Virtual particles pop in and out of existence, borrowing energy from uncertainty and paying it back. These virtual particles have real effects, measurable effects, from the Casimir force to the Lamb shift to the magnetic moment of the electron. Particles are excitations in fields that exist everywhere. You cannot remove the fields. You cannot stop the fluctuations. You cannot create true nothingness because quantum mechanics forbids it. The vacuum is a thing, a physical state with properties and energy and structure. Nothing is fundamental. Nothing is active. Nothing is everywhere. And this changes everything. It means the universe was never truly empty. Even before the Big Bang, there would have been quantum fields. Even in the emptiest regions of space, there is activity. Even in a perfect vacuum, there is something. The concept of pure nothingness, absolute emptiness, complete void, does not exist in our universe. It cannot exist. The laws of physics forbid it. Feynman understood this deeply. He spent his career working out the details, calculating the effects, making predictions that were confirmed by experiments. And he did it with a sense of joy, of playfulness, of genuine curiosity about how reality works. He wasn't afraid to say that quantum mechanics is weird, that it doesn't make intuitive sense, that you just have to accept the mathematics and the experimental results, even when they conflict with common sense. Here's something he said, and I'm paraphrasing because I want to capture the spirit of it. He said that nobody understands quantum mechanics. Not really. We have equations that work. We can make predictions. We can do calculations. But what it all means, what's really happening at the quantum level, is mysterious. And that's okay. That's wonderful. That's what makes physics interesting. The vacuum is like that. We know it's there. We know it has properties. We can measure its effects. But what is it really? What are quantum fields really? What does it mean for virtual particles to exist for a tiny fraction of a second? What is the nature of zero-point energy? These are deep questions, and we don't have complete answers. But here's what we do have. We have a framework, quantum field theory, that describes the vacuum and makes incredibly precise predictions. We have experiments that confirm those predictions to astonishing accuracy. We have a mathematical description that works, even if the interpretation is unclear. And that's progress. Real, meaningful progress in understanding what nothing actually is. Now, let me address something that might be bothering you. If nothing is something, if empty space is full of fields and particles and energy, then what do we call actual nothingness? What's the word for the complete absence of everything, including quantum fields? And here's the answer. There is no such thing. That state does not exist in our universe. It's not physically possible. It's not allowed by the laws of nature. True nothingness, absolute void, is not a thing that can be. It's a concept our minds can imagine, but it's not part of reality. It's like asking what's north of the North Pole. The question seems to make sense, but it doesn't. There is no north of the North Pole. There is no nothing beyond the quantum vacuum. This might frustrate you. Your brain wants there to be a concept of pure nothingness, of absolute emptiness. But the universe doesn't care what your brain wants. The universe is what it is. And what it is, at the most fundamental level, is quantum fields fluctuating in accordance with the uncertainty principle, creating a vacuum that's full of activity even when it appears empty.
Here's the beautiful part, and this is very Feynman.
Even though we don't fully understand it, even though mysteries remain, we can work with it. We can calculate with it. We can make predictions. We can build technology based on our partial understanding. Quantum field theory, the theory that describes the vacuum, is the foundation of modern physics. It underlies particle physics, condensed matter physics, cosmology. It's the framework for understanding reality at the smallest scales. And it all comes back to nothing. To understanding that empty space is not a passive backdrop, but an active participant in every physical process. That the vacuum has structure and energy and properties. That nothing is something. Let me tell you why this matters. Why does it matter that the vacuum is full of quantum activity? Because it means reality is fundamentally different from how it appears. It means the universe at its deepest level is quantum mechanical, probabilistic, uncertain. It means that existence itself requires quantum fields, requires fluctuations, requires the kind of nothing that's actually something. When you look at empty space, you're not looking at absence, you're looking at the ground state of all fields. You're looking at zero-point energy. You're looking at the substrate from which all particles emerge and to which they return. You're looking at the most fundamental thing there is. You're looking at nothing, and nothing is everything. This is what Feynman's answer to what nothing is would mess you up, because it's not what you expected. It's not simple, it's not intuitive. It's not the absence of things. It's a rich, complex, quantum mechanical state that's required by the fundamental laws of physics. It's measurable, it's active, it's everywhere. And we know this not through philosophy or speculation, but through mathematics and experiment. Through Feynman diagrams and quantum calculations and precision measurements, through the scientific method, through testing predictions against reality. The vacuum is real. Nothing is real. And it's nothing like what you thought. Here's my challenge to you. Next time you see empty space, next time you wave your hand through the air, next time you look at the gap between objects, remember, that's not nothing. That's the quantum vacuum. That's fluctuating fields and virtual particles and zero-point energy. That's the substrate of reality, the foundation of existence, the thing from which everything emerges. You cannot escape it. You cannot remove it. You cannot even properly imagine what it would be like without it, because without the quantum vacuum, there would be no particles, no forces, no structure, no universe. Nothing is required for everything. That's the paradox. That's the truth. Feynman would want me to end with this. Don't take my word for it. Look at the experiments. Look at the Casimir effect, the Lamb shift, the magnetic moment of the electron. Look at the precision of QED predictions. Look at the data. The evidence is overwhelming. The vacuum is real. Nothing is something. And it's one of the most well-established facts in modern physics. Your intuition is wrong. Your common sense is wrong. Your idea of nothing is wrong. And that's okay. That's part of learning physics, part of understanding reality, part of accepting that the universe is under no obligation to match your expectations. So what is nothing? Nothing is the quantum vacuum. Nothing is fluctuating fields at their ground state. Nothing is virtual particles and zero-point energy. Nothing is something active, complex, fundamental, and absolutely essential to everything that exists. Nothing is not the absence of everything. Nothing is the presence of something we're only beginning to understand. And that, right there, is what Feynman's answer would be. That's what nothing actually is. Not empty, not absent, not void. But full, active, quantum, and real. Nothing is something. And once you understand that, You can never look at empty space the same way again. That's the power of physics. Not just answering questions, but changing the questions themselves. Not just describing reality, but revealing that reality is stranger than we imagined. Not just explaining what things are, but showing us that the things we thought were simple are actually profound. Nothing is profound, and Feynman knew it. He calculated it. He predicted it. He tested it, and he was right. Nothing is not nothing. Nothing is quantum fields, uncertainty, fluctuations, and energy. Nothing is the foundation of everything. And that will absolutely mess you up if you really think about it. Welcome to physics. Welcome to reality. Welcome to understanding that nothing is something, and that something is more amazing than you ever thought possible.